Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about a crucial property of hypothesis tests, their power. The ultimate goal in hypothesis testing is to determine whether the available data supports a certain conjecture. The power of a test is the probability that we correctly identify that the conjecture holds when it in fact holds. It's the probability of a true positive. In this video, we're going to show how to compute the power of a test and also how to interpret it. Let's get to it. We're going to talk about the power of hypothesis tests, and to begin, let's remind ourselves of how the framework of hypothesis testing works. In hypothesis testing, we begin by choosing a certain conjecture of interest. Then we choose a null hypothesis that contradicts that conjecture. We also choose a test statistic that should be large if the null hypothesis does not hold. A large test statistic is evidence in favor of the original conjecture. Then we decide on a significance level alpha, which is often set at 5%. We gather the data, compute the test statistic, and then compute the p-value corresponding to that test statistic. If the p-value is smaller or equal to the significance level alpha, we reject the null hypothesis. When we reject the null hypothesis, that means a positive finding, because rejecting the null hypothesis is evidence in favor of the original conjecture. If we carry out all of these steps, we have seen in a previous video that the probability of a false positive, which means that we reject the null hypothesis but it actually holds, is bounded by the significance level alpha. For example, 5% if that's what we chose. The whole framework of hypothesis testing is set up so that the probability of a false positive is controlled. It's bounded by this predefined significance level. However, is that enough? Is it enough to just control false positives? Well, it is not, right? Because there's a trivial way of controlling false positives, which is never to reject the null hypothesis, never to find a positive finding. In that case, the probability of a false positive is going to be 0, but we're never going to be able to decide that we have enough evidence in favor of our original conjecture, so the whole endeavor is meaningless. We need to make sure that we find true positives. And the power is the probability of a true positive. This is why it's a crucial property of hypothesis tests. We're going to be working within the framework of parametric testing, where we assume that the test statistic follows a distribution that depends on certain parameters, theta. We're going to define the power function as the probability that we reject the null hypothesis for a certain value of the parameter, when the test statistic is distributed according to a certain value of theta. Remember that we reject the null hypothesis when the p-value is smaller or equal to alpha, and the p-value at the end of the day depends on the test statistic. So here the test statistic is distributed according to this value of theta. It gets plugged into the p-value function to obtain the corresponding p-value, and if that is more or equal to alpha, we reject. This is a function from theta to the probability of rejecting when the test statistic is distributed according to that value of theta. The name power function can be a little bit confusing because it's also defined for values of theta that correspond to the null hypothesis. If the value of theta is within the null hypothesis, then rejecting the null hypothesis results in a false positive. So for those values, the power function is actually the probability of a false positive, and we have already mentioned that it's going to be bounded by alpha, as we established in the video on statistical significance. More interesting is the case where the parameters are within the alternative hypothesis, that do not belong to the null hypothesis. For those values of the parameters, if we reject the null hypothesis, we have a true positive. For those values, the power function gives us the probability of a true positive, and this is what we want to maximize. This is the power. Now we're going to derive the power function for a specific example so that this becomes clearer. So the example that I have chosen is this die example, where I took a toy die from my daughter. My conjecture is that the probability that we obtain a 3 it's a 6-sided die. Okay, so my conjecture is that obtaining a 3 is more likely than other numbers, or equivalently that the probability of rolling a 3, which we're going to call theta, you can already see that this is going to be our parameter of interest, is greater than 1/6. Here, the null hypothesis is very natural. It's the probability, the null hypothesis is that this probability is smaller or equal to 1 over 6 as opposed to being greater than 1 over 6. So you can clearly see that it contradicts the original conjecture. Now the test statistic should be large if the conjecture holds and if the null hypothesis does not hold. So it's very natural to choose the number of threes. The number of threes is large. That probably indicates that indeed theta is greater than 1 over 6. The distribution of the test statistic is binomial under the assumption that the die rolls are independent, and we're going to assume that each die roll has the same probability of being a 3, which we call theta. Here we have this parametric distribution for our test statistic, so we're ready to compute the power function. The power function is the probability that we reject the null hypothesis for a specific value of theta, as a function of theta, as a function of the probability that the die lands on a 3. This is the probability that the test statistic, which is the number of threes, and the number of threes when the probability of a 3 is equal to theta. If we plug in that test statistic into the p-value function, the corresponding p-value is smaller or equal to alpha. We're going to show now in the next slide that this is completely equivalent to saying that the test statistic, the number of threes, is above a certain threshold. And we want to rewrite it this way because it's going to be much easier to compute. But let's establish that that is indeed the case. We're going to define something called the rejection region, which is the values of the test statistic for which we reject, for which the p-value is smaller or equal to alpha. Remember that the test statistic is just the number of threes that we see. If the number of threes is above a certain threshold, then the p-value is going to be below alpha. For example, if we had chosen alpha to be 0.05, the p-value will be below 0.05 and we will reject. Now we want to find what is this threshold. By definition, the threshold is the minimum value of the test statistic for which this happens, for which we reject. The p-value is smaller or equal to alpha. Let's establish that the threshold is well defined in the sense that we reject if and only if the test statistic is greater or equal to the threshold. First of all, if the test statistic is below the threshold, then by definition, because this is the minimum value for which we reject, if the test statistic is below the threshold, we don't reject. Okay, so we have the implication in that direction. Now let's see what happens if the test statistic is above the threshold. Then we do reject, because what is the probability that the test statistic is above the threshold? It can only be smaller than the probability that the test statistic is above this tau that is greater than the threshold. The probability that the test statistic is above tau that is greater than the threshold is bounded by the probability that the test statistic is greater or equal to the threshold, because this is, because here we're assuming that tau is greater than tau threshold. So let me get this right. If this happens, then definitely this happens. So the probability of this event is greater than the probability of this event. It's easy to get, I always get confused by this, but basically what we're saying is if a certain threshold is the probability at which the smallest test statistic at which we reject, the smallest number of threes at which we reject the null hypothesis, if we see a greater number of threes, we're also going to reject. Okay, so that makes a lot of sense. Okay, so, and this is going to be, this inequality immediately implies that we reject because we know that for the threshold, that probability is, the p-value, is more or equal to alpha. Okay, hopefully this is clear. This is the p-value for tau, and this is the p-value for the threshold. Okay, so we have established that if we're above this rejection threshold, this number of threes that we need to roll in order to reject the null hypothesis, we reject the null hypothesis. Now, how do we compute this threshold? Well, it's the minimum value of the number of threes such that the p-value is more or equal to alpha. But we can actually write the p-value in terms of the PMF. Okay, the probability that this guy is greater than tau is just the PMF summed from tau to n, okay? And we need that to be small or equal to alpha. So we can just compute this for all the possible values of tau and check what is the smallest one where we are below alpha. If we do that, and here just showing you that we are plugging in 100 because we have 100 die rolls, and our theta null, the theta null, which is going to limit this, is going to be 1/6, because remember that the null hypothesis is that theta is smaller or equal to 1/6, and this is the largest value that we can attain for that probability within the null hypothesis. If we compute this for all the possible values of tau and find the smallest one, if alpha is equal to 0.01, we see that we reject when the number of threes is 27 or more. Remember that what we actually observed were 21 threes. So in this case, we would not reject for this significance level. If the significance level is greater, then the minimum is going to be smaller, right? So for 0.05, the threshold is at 24. We also don't reject, I said this really quickly, but we observed that there were 21 threes in the actual data that I gathered. So we didn't reject the null hypothesis, and here you see why. Our significance level in the previous video was 0.05. If we increase it up to 0.25, then we would reject, because the threshold would be 20. Okay, so hopefully this clarifies how we find this rejection threshold. The rejection threshold is going to be useful to compute the power function. Realize that the rejection threshold only depends on the null hypothesis. Okay? Only depends on the values of the parameter for the null hypothesis. But now the power function gives us information about any value of theta. So we want the probability of rejecting the null hypothesis for any value of theta. That's the probability that the test statistic for any value of theta, it's no longer just for the null hypothesis, is greater or equal to the threshold that we have found using the null hypothesis. Okay, for example, for 0.01, what's the probability that for some other value of theta we're above 27? This is how we find the power function. Now we use the fact that we have the distribution, the PMF of our test statistic as a function of theta, and we want the probability that we're larger or equal to this threshold. So we plug in the threshold there. This threshold was computed from the null hypothesis, but now the power function is not computed only from the null hypothesis, it's computed for an arbitrary value of theta. I really want to emphasize that, because we want the probability of rejecting the null hypothesis for some arbitrary value of theta, including the ones in the alternative hypothesis. If we plug in n equals 100, then we obtain this power function. And now we're going to take a little bit to really understand what the power function is telling us. We're showing you the power function for three values of alpha, okay? 0.01, 0.05, and 0.25. Now let me go back to this point about the null hypothesis and the alternative hypothesis. In our problem, the null hypothesis is that we're smaller or equal to 1/6. And the alternative hypothesis is that we're above 1/6, that theta is above 1/6. Okay, to begin with, let's draw a line here exactly at theta null. We're calling here theta null 1/6. It's the limit at which the null hypothesis changes into the alternative hypothesis. So let me draw a line upwards here. Remember that the power function tells us the probability of rejecting the null hypothesis. So here, this probability should be below the significance level. Let's check that that is indeed the case. And what we see is that indeed here the highest value is 0.25, which is exactly the significance level. Here the highest value is 0.05, which is indeed the significance level. And we don't see 0.01 because it's there, but you can trust me on that. Okay, so we see that in this region, indeed, the probability of rejecting, which is what the power function tells us, is bounded by the significance level. We're good. Now let's talk about the actual power, which is what happens, let me change the colors, which is what happens when theta is within the alternative hypothesis, which is that actually the probability of rolling a 3 is higher than 1/6. Then these curves tell us the probability that we actually detect that with our hypothesis test. Let's take a look at what happens if the probability of rolling a 3 is 1/4. okay, this line is a bit like, let me move it a little bit. Yeah, 1/4 is more or less there, okay? So that's the probability of rolling a fourth. What's the sorry. If the probability of rolling a 3 is 0.25, is 1/4, how often do we actually detect this with our hypothesis test? Well, if we set our, let me erase this. If we set our significance level to be 0.25, then we detect it, 90% of the time. So that's pretty awesome. But we have a probability of 1/4 of a false positive. So that's the flip side. If our significance level is 0.05, which is what we chose, then we're going to detect it about 65% of the time. So it's very likely, well, it's very possible that we'll miss it. And this, I think, what happened in our situation, where I rolled 21 threes and it was below the significance level, but I still think that the alternative hypothesis probably holds. And then if we're very strict with our significance level, then here the probability of actually detecting that the die is biased, if the probability of rolling a 3 is 0.25, is 1/4, is below 50%. It's like around 40%. Of course, if it happens that the die is very biased, so the probability is 1/3, then we have much more power, right? For all the significance levels, the probability of detecting it is very high. Okay, for 0.01, it's still maybe, 90-something%, but for the others, it's almost 100%. Okay, so this tells us for what values of theta, of the probability of rolling a 3, we're likely to actually detect that the die is biased, that the alternative hypothesis holds for the different significance levels. So let's talk a little bit more about the dependence on alpha, because we have seen here that there is a clear dependence on alpha on the significance level for our power function. For any alpha 1 and alpha 2 such that alpha 1 is smaller or equal to alpha 2, if we're stricter with our significance level, then the probability of rejecting is smaller than if the significance level is higher. So we get more power, as we just saw, if alpha is higher. So shouldn't we just make alpha super high? What's the problem with that? I would like you to pause the video and think about that, because I kind of hinted at it a moment ago. Well, the issue is that indeed you can see that for higher alpha, the power goes up. That is true. But the probability of a false positive also goes up. In fact, the probability of a false positive is equal to alpha. So here, if we set alpha to 0.25, 1/4 of the time we're going to be saying that the die is biased, but it is actually not biased. And again, the hypothesis testing framework is set up so that we avoid false positives. So this is not very satisfying. There's this inevitable inevitable trade-off between probability of a true positive and probability of a false positive. How can we break that? What can we do to actually increase power while keeping alpha fixed so that we are still controlling the probability of a false positive? Well, you can do this by gathering more data. Often in data science, the answer is actually just gather more data. So here, let's take a look at what happens if we fix the significance level at 0.05. This is why you see here. Let me quickly remind you that this is the null hypothesis up to here, and this is the alternative hypothesis. And here I'm showing you what happens for n equals 20. In our case, we had 100 rolls. So n equals 20, n equals 100, and n equals 500. We're always guaranteed to be bounded. Okay, the null hypothesis is up to here. We're always guaranteed to be bounded by 0.05 within the null hypothesis, because that's how the hypothesis testing framework is set up. But when we have more data, we see that the probability, let's take a look at 0.25 here. So basically there's 1/4 probability of rolling a 3. Then if we don't have enough data, here most of the time we're actually not going to correctly detect that the die is biased. Okay, so for n equals to 20, for, and now I'm mixing colors, red and, yeah, I'm sorry that I drew that in red. Let me switch that to blue. So if we only have 20 data points, then 1/4 of the time, even if the probability of rolling a 3 is 0.25, we're not going to have a true positive. This goes up to almost, 65%, 0.65. If we have 100 die rolls, still not super satisfying because, realize that the difference between 1/6 and 1/4 is actually pretty large. So this is a very biased die. But if we have the patience to gather 500 die rolls, then the probability of detecting it is almost 1. We're almost sure to detect it. So this essentially demonstrates that my experiment with the die rolls did not have the sufficient power. In the literature, this is called when a study is underpowered because we don't have enough data to ensure that the probability of correctly identifying a positive finding is high enough. Obviously, I didn't have the patience to go and roll the die 500 times, so we'll have to, we will never know if the die is actually biased or not. Okay, so now let's consider a different situation. This is an example that we used to illustrate two sample tests. Here, our conjecture was that Giannis Antetokounmpo, who is one of the top players in the NBA, our conjecture was that his free throw percentage was different at home and away. And our null hypothesis was that the percentage is actually the same. Our test statistic was the percentage at home minus the percentage away. But here we had a choice to make because we could take just the difference like that because we assume that if one of the two percentages is higher is going to be at home where people are not yelling at him. Remember that part of the motivation is that when he plays away, people yell 1, 2, 3, 4 while he's attempting to throw a free throw because his free throw shooting is not that great and people want to pressure him and he takes very long. Okay, go watch the video on the two sample tests if you want to know more about that. The other choice is to use a test statistic that is the absolute value. So this test statistic is also going to be large if for some reason his away free throw percentage is higher than his home free throw percentage. But this is not the case for this guy. So now we can use the power function to compare these two tests. Just to be clear, we have the same. So basically, we showed this in the video on two sample tests. We showed that the test statistic is approximately Gaussian under certain assumptions, and for the one-tail test, where we just have the difference between the home percentage minus the away percentage, we took one tail to compute the p-value, and our p-value was equal to 0.0111. In the case of the two-tail test, where we also consider cases where the away percentage is higher, then we took the two tails of the test. Okay, this is just to visualize what's going on. Remember, this is the distribution of the test statistic under the null hypothesis. Okay, so we're going to show you the power function. Here we have, like when the alternative hypothesis holds, we actually have two parameters. When the null hypothesis holds, we just have one parameter, which is the probability of making a free throw. When the alternative hypothesis holds, we have two different parameters, the home percentage and the away percentage. In order to be able to plot the function in a way that is easy to visualize, what we're going to do is we're going to fix the home percentage to be the season percentage of Giannis Antetokounmpo, and we're going to see how the power function changes as the away percentage changes. Okay, we're going to show you the power function as a function of theta away. I'm not going to show you the whole derivation because it's very similar to the die example and not super interesting, but we also find a rejection region, and then we just compute the probability that for other values of theta, in particular theta away, we reject the null hypothesis. So let's take a look at the results. Here I'm showing you the one-sided test as this solid line and the two-sided test as this dotted line. So first, let's remind ourselves that here, this is the null hypothesis. The null hypothesis is that they're the same. And as we see, the power function is bounded by 0.05 at the null hypothesis because that's our significance level. So the things are, if you plot a power function and at the within the null hypothesis, when the parameter corresponds to the null hypothesis, it's not bounded by the significance level, something has gone wrong. So that's an easy sanity check if you're deriving power functions. Let me remind you that this is the null hypothesis because this is exactly where theta home and theta away are the same. Everywhere else, it's the alternative hypothesis. So now let's see the probability that we identify that using the two tests. Let's see first what's the probability of identifying that Giannis actually shoots differently when his free throw percentage away is just 0.5. So it's much smaller than 0.65, which was the percentage at home. Let's see if I said that correctly, 685, okay? So here, what happens when the percentage away is 0.5, which is much smaller? Well, what we observe is that with the two-sided test, we're going to reject 1/2 of the time. And with the one-sided test, we're going to reject almost 60% of the time, so 10% more. So in this case, here, the one-sided test has more power. So is the one-sided test just better in general? Well, it depends, right? Because here, if it turns out that Giannis actually shoots very well away for some strange reason, he gets very motivated by people yelling at him, then with the one-tail test, we're never going to find this. Why? Because the one-tail test is the percentage at home minus the percentage away. If the percentage away is higher, it's negative. The test statistic is never going to be greater than whatever threshold. The p-value is never going to be smaller, okay? So basically, the one-tail test does not detect this situation. It has no power over here. But the two-tail test does have power over here. So here we see that more than 50% of the time we would be able to detect this. So here you can see that the power function allows you to detect, to quantify for what values of the parameter under what assumptions we're going to be able to find true positives when they actually hold. And depending on the different situations, you might be interested in having more power in certain regions or in others. Here I would argue that it was pretty clear that we would think that he would shoot better at home, so we might go for the one-sided test that gives us more power here. What happens when, so I have shown you how to derive the power function analytically for the die example. It gets a little bit complicated and the die example is super simple. So what happens when it becomes so complicated that we cannot really derive these power functions analytically? What can we do? Well, we can estimate them using the Monte Carlo method. How do we estimate the power using Monte Carlo simulations? Well, we need to be able to simulate the test statistic for any value of theta. So here let's fix a value of theta, and we're going to we're going to estimate the power for that specific value of theta. We need to be able to simulate the test statistic for that value of theta, and what we do is we simulate it many times. And then what is the power? The power is the probability that the corresponding p-value is smaller or equal to alpha. So we compute the p-value for all of these guys and just check what fraction is below the significance level alpha. And that is going to give us an approximation of the probability that the p-value is below the threshold, hence the probability that we reject the null hypothesis, and that's exactly what the power is. So this is how we use the Monte Carlo method to estimate power. Let's take a look at an example for Giannis's free throw, the Giannis free throws example. Use example 20 times there, sorry about that. What happens when the null hypothesis holds, okay? Theta away is equal to theta home. Here, we're just going to simulate free throws, okay? We're going to simulate free throws, assuming that they're the same. And this guy, remember, is fixed to 0.685. This is the distribution of the p-values corresponding to the value of the test statistic for the one-tailed test, okay? So basically, we simulate, I forget what was the total number of free throws. It was like 80-something, I think. So we simulate 80-something free throws. I think it was something like 41 away and 43 at home, something like that. And then we compute the difference between the fraction of free throws that he makes at home and the fraction that free throws that he makes away. And then we compute the p-value corresponding to that difference, corresponding to that test statistic. This is a distribution of the p-values. As you can see, it looks approximately uniform, which is exactly what we proved would happen when the null hypothesis holds, okay, in the video on statistical significance. And the p-value that we obtain is basically the fraction of these guys, of the p-value, not the p-value that we obtain, sorry. The value for the power, our estimate of the power, is going to be the fraction of the p-values that end up below the significance threshold. In this case, it's almost 0.05. This is exactly what we expect. When the null hypothesis holds, the power function is equal to the significance level. What happens if the percentage of away free throws is 0.55, which is smaller than the home free throws? Well, we do the same thing. Now we plug in this different percentage, we compute the test statistic, we compute the p-values corresponding to the test statistic, and what do we see? That, many more of the p-values are below the significance threshold. The percentage is actually 33.9%. So that is the power. That is the probability that we reject the null hypothesis for this percentage of away free throw percentage of away free throws. And finally, we can also see what happens if the percentage is higher away than at home. So maybe think about what you expect to see here. A hint, we're using the one-tailed statistic. So remember that the one-tailed statistic is not sensitive to this. So the p-values are all very large. The test does not see what is going on because the p-value is only small if the test statistic is large, and here we're doing the observed percentage at home minus the observed percentage away. So if the away percentage is very large, then we get a negative test statistic. The p-value, the probability that the p-value is below the significance threshold is very, very low. Okay, indeed here the power is 0.011. The test is completely underpowered to detect situations where he's shooting better away than at home. Okay, so what have we learned? We have learned the definition of power. We have learned how to, the definition of power function, which is defined for the null hypothesis and also for the alternative hypothesis. We have derived the power function for a parametric test. We have shown how to interpret it. And then we have shown you how to estimate the power using Monte Carlo simulations. And that's all I have. Thank you very much.